Example 10 is a related rate problem, and it gives us an equation, x cos y squared equals y, and it says a particle travels along a path described by that function. So it moves horizontally at a constant rate of 3 meters per second, and we want to figure out the vertical rate when the particle is at 0, 0. So first of all, this xy equation is an implicit function that only describes the path. The rate comes into play here at 3 meters per second. That is a dx by dt. So whenever we introduce t into here, we need to kind of recall that this is a related rate problem and we need to differentiate with respect to time. Okay, so this is going to be an implicit function which I'm going to differentiate with respect to time. Now there's a few things going on here. There's a product and an embedded function, so I have to remember to use chain rule. So in differentiating this, I'm going to first start off by differentiating the left-hand side. When I differentiate this implicitly, I differentiate the x. I'm going to generate my dx by dt. Okay, so the derivative of x is dx by dt times cosine of y squared plus x times the derivative of cosine is negative sine y squared. But because y is embedded, I need to apply chain rule, so I end up with times 2y. And since the y is embedded in all of that, I need to then apply the chain rule again. This is where my dy by dt comes into play. Okay, so this is what I need to solve for. This is what I'm trying to find. And that is the product rule for the left-hand side of that equation. On the right-hand side, I'm going to differentiate y, and again, I'm going to differentiate y becomes 1 times the derivative of y with respect to time. Okay, so now I've differentiated this expression with respect to time. Now, I could solve for y prime, but it might be easier in this case to plug in the 0, 0 because that's going to generate a lot of zero parts to this. Okay, so I'm going to have dx by dt, which I know is going to be 3 cosine of 0 squared, so that's going to be cosine 0, plus x is 0, so I'm going to plug in my 0 here. I'm going to maybe keep track of my signs here, so that should be minus for the sign. So I end up with sine y squared is 0, so I'm going to generate a 0 here. So I have 0 factors here, so I don't have to worry about this whole entire expression. This is just going to end up being 0. So this dy by dt just disappears. Okay, and then on the right-hand side, I have my dy by dt, and that's what I'm solving for. Okay, so there's my derivative. I've differentiated implicitly. I recognize it's a related rate problem. I need to differentiate with respect to time. And then I've plugged in my zeros. This is just going to make the dx by dt. We've established that that's 3 meters per second. Cosine of 0 is equal to 1. Minus, well, these are 0 factors, so that all becomes 0. And that's equal to my dy by dt. So this is what I'm looking for, the vertical rate at that point. So dy by dt then works out to be equal to 3 meters per second. Okay, so we're going to graph this. And when you take a look at the graph of this, you'll see that the slope through that point is going to be a slope of 1. So that's why the horizontal component the horizontal speed is the same as the vertical speed. So looking at that function, x cos y squared equals y, we can see that at 0, 0, the tangent line looks like it's about 45 degrees. So the rate at which it's moving horizontally is going to be equal to the rate at which it's moving vertically. This problem involves the definition of derivative. So we've been defined an f function as e to the x, and we need a limit expression equal to f prime of e. And these are going to be using the definition of the derivative. So we kind of got to think of what this might look like. So we have our e function. It's going to go through like that. We have some point at e. Okay, so this is going to be e to the power e. And to make this a definition of derivative, we need a point just a little bit further away. And that's going to be some point e plus h to give us our run and rise. And this coordinate here must be e to the e plus h. So of these expressions, we can kind of see that a is probably not a good option. And the reason it's not a good option is because there's not even a slope ratio that or difference that we're finding in A. The rest of them do have differences, but we have to make sure we know which one's going to generate the slope at E. So looking at D and B, we can see that they have x's in them. So these are going to generate general expressions or functions of x. And we actually want the actual slope at E when we have this expression over here. Okay, so we're left with C and E, and we can see that based on our slope formula, well, we're going to have our rise is going to be e to the e plus h minus e to the e, and that's going to be divided by the run, so that's going to be this answer here. And this one's just missing. This coordinate doesn't match this coordinate here, so that one is going to be one that we need to eliminate as well. So the answer is E.